You've probably heard the big news by now. NASA may have found a possible sign of life on Mars. These tiny marks, almost too small to see, are the most significant space discovery in over 50 years. If this truly is evidence of life, it would be the most important find in human history. But we've gotten our hopes up before, only to be disappointed. So, is this finally the real deal? Let's explore what the Perseverance rover discovered, why researchers are so excited, and what it will take to confirm we're not alone in the cosmos. In February 2021, NASA's Perseverance rover, nicknamed Percy, landed in an ancient Martian lake bed. This area, called the Jezero crater, was once filled with water. Rivers flowed in and out, shaping deltas and depositing sediment. The ground is full of clay minerals that only form where water is present. Percy's mission is to search for signs of ancient microscopic life. If it's going to find it anywhere, the Jezero crater is a perfect place to look. Ancient lake beds on Earth often contain chemicals called perchlorates, which certain microbes can use for energy. Scientists who study life in extreme environments on Earth examine similar microbes to understand if life could survive on other worlds. The rover's job is to look for these potential biosignatures, identify and collect the most interesting rock samples, and prepare them for a future mission to bring them back to our planet. One day in July 2024, while exploring the edge of an old river channel known as Neretva Vallis, Percy's cameras noticed something odd. It was a rock from a formation called Bright Angel. Two of the rover's instruments detected that the rock was made of clay and siltstone. On our planet, these materials are excellent at preserving traces of microbial life. So Percy took a closer inspection. What it found was remarkable. The rock, also referred to as Cheyava Falls, was packed with organic compounds like carbon, phosphorus, and iron, arranged in circular patterns. Scientists have playfully named these patterns leopard spots and poppy seeds. They are incredibly small, ranging from 200 micrometers to 1 millimeter across. But this was enough to get astrobiologists around the world very excited. The light-colored center of a leopard spot has a similar chemistry to the surrounding rock, but the dark outer ring is enriched with iron and phosphorus. This appears to be evidence of a process called localized iron reduction. Percy also found carbon-based organic compounds in the rock. Based on its texture and chemical makeup, there is a strong suspicion that this rock was once in contact with liquid water. Typically, when we see this specific combination of organic material, water, and iron reduction on Earth, it is interpreted as a sign of past microbial activity. Suddenly, NASA had something incredibly unique. Could this mudstone hold the first alien biosignature ever discovered? Two special minerals are central to this story: Vivianite and Greigite. Vivianite is an iron phosphate mineral. On Earth, it forms near metal ores and river sediments where microbes, such as geobacter, use iron for energy instead of oxygen. They take in one form of iron and release another as waste. The energy from this reaction fuels their metabolism, a process known as chemosynthesis. When the expelled iron reacts with phosphate and water in the environment, it creates Vivianite. Greigite has a similar origin story. On Earth, microorganisms that reduce sulfate break it down into sulfide, which then reacts with iron to form Greigite. But let's be skeptical for a moment and set aside the microbial explanation. What else could have caused these chemical reduction reactions? One possibility is extremely high temperatures. The sulfide needed to make Greigite could have come from volcanic gases seeping into groundwater. However, that would require the sulfide to travel from a hot volcanic system into a much cooler setting, and there's no evidence of such volcanic sources nearby. Another idea is that sulfate in the rocks was reduced to sulfide through reactions with organic matter, but unless temperatures were above 150 to 200 degrees Celsius, these reactions would be extremely slow and require a massive amount of energy, making them very unlikely. Studies of the rocks in this area show no signs of ever being exposed to such high heat. So, it's improbable that the environment got hot enough to form Greigite this way. Acidity is another potential explanation. Both iron and sulfate ions dissolve much more easily in acidic water than in neutral water, making them more prone to reduction through simple chemistry. If the water on Mars was more acidic than we thought, that could have created the spots Percy observed. Perhaps these features were just the result of chemical processes on an alien world, nothing more. But then, Percy spotted a small green mineral nearby. A little piece of olivine rock, found close to the sample site, challenged the acidic water idea. Olivine is the fastest weathering type of silicate mineral. Unlike other structures, it doesn't have strong bonds between silicon and oxygen atoms. Instead, it's made of silicate ions held together by attraction to magnesium and iron ions. In acidic conditions, hydrogen ions displace these, breaking olivine down. The more acidic the environment, the more hydrogen ions are present, and the more aggressively the olivine would dissolve. So, the simple fact that this olivine exists rules out the possibility that highly acidic conditions created the strange spots. The heart of the scientific method is falsification. It's not about proving something true. More often, it's about proving other explanations false. Over time, through a process of elimination, all paths seem to lead to the same conclusion. And if that conclusion withstands enough scrutiny for long enough, it eventually becomes an accepted theory, something testable, reliable, and widely agreed upon by scientists. In the recent research paper, the Mars team tried to prove that these minerals were not left by ancient alien life. They started with the assumption of no life and systematically investigated every non-biological explanation for what they found. But after months of study, they concluded they simply couldn't rule life out. For one, all our speculation and cautious excitement is based on what we know about biochemistry on Earth. No matter how tempting, we can't assume that just because something happens one way here, it would happen the same way on Mars. Maybe Mars has a completely different biochemistry we know nothing about. NASA is being very careful not to jump to conclusions. After all, we've been wrong about potential signs of life on Mars before. Back in 1976, the Viking lander tested Martian soil by adding nutrients tagged with a radioactive form of carbon. If microbes were present, they would metabolize the nutrients and release radioactive carbon dioxide that could be detected. To everyone's amazement, that's exactly what seemed to happen. Excited researchers thought they had proof of alien life. But in 2008, NASA's Phoenix lander found the Martian soil was rich in perchlorate, a powerful chemical that destroys organic material and releases gas when heated. What looked like biology was actually just chemistry, a false positive. Mars has continued to tease us with hope. In 1996, a meteorite from Mars, known as ALH 84001, made headlines. The rock itself was over 4 billion years old, from a time when Mars had liquid water. Under powerful microscopes, Tiny structures appeared that looked like fossilized bacteria. The world was captivated. Scientists believed they were onto something monumental, so much so that President Bill Clinton made a formal announcement about the discovery. This sounds a lot like the recent statement from NASA about Percy's find, doesn't it? But in 2022, those squiggly shapes were determined to be non-biological, explained instead by a water-rock interaction. Another false alarm. So, is this new finding in the Jezero crater another near miss? Or is it proof that the third time's the charm? There's only one way to know for sure. We must bring the sample back to Earth for more advanced testing. This is where the Mars sample return mission comes in. It's an incredibly complex operation requiring 3 separate spacecraft. Percy has already completed Phase 1. It drilled into Cheyava Falls and sealed away a precious core sample of the mudstone, which mission scientists named Sapphire Canyon. Phase 2 would involve sending another spacecraft to land near Perseverance, collect those sample tubes, and launch them into orbit around Mars. The third and final craft would retrieve the samples from orbit and carry them all the way back to Earth. It's a massive undertaking with an estimated cost of $11 billion. The Mars sample return mission was first announced in 2022 as a joint project between NASA and the European Space Agency. Since then, it has faced major financial challenges and uncertainties, pushing the timeline from 2033 to 2040 before being suspended indefinitely. This is despite the National Academy of Sciences Decadal Survey, a meeting of top scientists who set priorities every 10 years, naming Mars sample return as NASA's highest priority for 2 decades in a row. And that was before this potential biosignature was discovered on our neighboring planet. All we can do is hope this finding creates enough political pressure for leaders to mobilize the resources needed to make it happen. So, if we ever do get the Sapphire Canyon sample back to Earth, what kinds of tests might scientists perform? Among other analyses, they will likely look for 2 key fingerprints of life. The first is chirality. Amino acids, the building blocks of life, come in 2 mirror image versions, right-handed and left-handed. On Earth, life overwhelmingly uses the left-handed versions, while non-living materials show a more even split. If the Martian sample shows a strong preference for one version over the other, that could be a major clue. The second fingerprint involves carbon isotopes. Carbon atoms come in different forms, most commonly carbon-12 and carbon-13. Life strongly prefers carbon-12. The ratio of carbon-12 to carbon-13 in living things is much higher than in non-living matter. If we see a similar pattern in the Sapphire Canyon sample, that could be another strong indicator of a biological origin. We often think of discoveries like this in a binary way. Either it's life or it isn't. But NASA has a more nuanced approach. They recently proposed the Confidence of Life Detection Scale, a framework for ranking how likely a discovery is to be a sign of life. NASA hasn't stated where the Jezero crater discovery falls, but it's likely somewhere between levels 3 and 4. If the samples return and independent labs worldwide confirm a biological origin, that would push us up to a level 6. Level 7 might even require going back to Mars and finding the same evidence in a completely different location. So, when NASA says this could be the clearest sign of life ever found on Mars, they don't mean it clearly is life. But the Mars sample return mission could finally answer whether we've always been alone in the universe, or if we once had a neighbor next door. Even if the sample turns out not to be from life, it's still an extraordinary discovery that will help us understand our own origins better. We think of Mars as a time capsule of early Earth. Unlike our planet, Mars doesn't have continental drift or active plate tectonics. Its crust has been frozen in place for billions of years, preserved in a way Earth's crust never could be. Ancient landscapes on Earth have been erased by tectonics, erosion, oceans, and volcanoes. So, when we study Mars, we're not just asking if it once had life. We're also looking at a record of planetary conditions that resemble Earth at the dawn of biology. In that sense, Mars is a window into our own beginnings, offering clues to what Earth might have been like before life changed it forever. But let's dream for a moment. What if the sample does turn out to be from life? Most immediately, it would mean Mars was habitable for much longer than we thought, since the sample comes from relatively young sediment. And in doing so, open a huge box of new questions. Did life on Earth start on Mars, or vice versa? Did a meteor from interstellar space seed life on both planets? Or did life arise spontaneously, independently, in two different places? Where else could life exist in the universe? How common is it, really? This would also have implications for the Drake equation, a formula used to estimate the number of intelligent civilizations in our galaxy. One factor in the equation represents the fraction of habitable planets that actually develop life. If both Earth and Mars independently gave rise to life, this value would jump from being considered very small to being much closer to 1. An increase here causes the estimated number of civilizations to shoot upward. However, this only changes if life on Earth and Mars arose independently. If we're related, the products of life spreading between planets, a concept called panspermia, that still represents just one origin event, and the outcome of the equation stays the same. There's a concept known as the 0-1 infinity rule in astrobiology. It suggests life can only exist in 0, 1, or an infinite number of places. We already know it's not 0. If it's just 1, then we are alone, a single spark in the darkness. But if it's 2, Earth and Mars, then why not 5, 5,000, 5 million, or even an infinite number of places in the cosmos? Suddenly, life isn't rare. We're not special anymore. And many hope that if we ever do discover life out there, it might just bring us closer together right here on Earth. If you found this journey into a potential cosmic discovery fascinating, help us share the wonder. Give this video a like, subscribe for more explorations of our universe, and share it with someone who loves to ponder the big questions, not special anymore. And many hope that if we ever do discover life out there, it might just bring us closer together right here on Earth. If you found this journey into a potential cosmic discovery fascinating, help us share the wonder. Give this video a like, subscribe for more explorations of our universe, and share it with someone who loves to ponder the big questions,